A black hole the size of 1 billion suns shouldn't exist when the universe is barely a tenth of its current age. Physics says no. Formation timelines say impossible. Every model we had insisted these titans needed eons to grow. Yet James Webb is staring at them. Supermassive black holes fully formed just a few 100 million years after the Big Bang. Not growing slowly over cosmic time. Already there, already massive, already defying what we thought we understood. Scientists just revealed these monsters can form in as little as 100 million years, and the method is so extreme it rewrites the rules of cosmic evolution. If you're curious how the universe breaks its own limits, subscribe and hit that like button. Let's uncover what James Webb found lurking in the infant cosmos. To understand why finding supermassive black holes in the early universe is so shocking, we first need to appreciate just how difficult it is to build something that massive in such a short time. Black holes are not rare. They exist throughout the cosmos in various sizes. Stellar mass black holes form when massive stars collapse. These typically weigh between a few and a few dozen times the mass of our Sun. They are common, well understood, and their formation process is relatively straightforward. A star exhausts its fuel, its core collapses, and if the mass is sufficient, a black hole emerges. This happens routinely across galaxies. But supermassive black holes are an entirely different category. These are not just bigger versions of stellar black holes. They are fundamentally different beasts. Supermassive black holes weigh millions to billions of times the mass of the Sun. They sit at the centers of most galaxies, including our own Milky Way. Our galaxy's central black hole, Sagittarius A star, weighs about 4 million solar masses. That is enormous compared to a stellar black hole, but still modest compared to the giants found elsewhere. Some supermassive black holes weigh tens of billions of solar masses. Their gravitational influence shapes entire galaxies, controlling star formation, gas dynamics, and even the fate of stars orbiting nearby. For decades, astronomers assumed these giants grew slowly over billions of years. The standard picture was straightforward. A stellar mass black hole forms from a collapsed star. It then begins accreting matter, pulling in gas and dust from its surroundings. Over time, it grows. It merges with other black holes when galaxies collide. Slowly, incrementally, it gains mass. This process takes time, a lot of time, billions of years, and that timeline made sense because the universe had plenty of time to spare. The cosmos is roughly 13.8 billion years old. If supermassive black holes needed billions of years to grow, that was fine. The universe provided the runway. But then observations began revealing something deeply troubling. Supermassive black holes were being detected in the early universe, not just moderately large ones, but fully formed monsters weighing billions of solar masses, and they were found at redshifts corresponding to when the universe was less than 1 billion years old. Some appeared when the cosmos was only 700 million years old. A few were detected even earlier. This created an immediate problem. If these black holes needed billions of years to grow, how could they already be so massive when the universe itself was barely out of infancy? The tension was not subtle. It was a fundamental contradiction. The growth rate required to build 1 billion solar mass black hole in less than 1 billion years far exceeded what standard accretion models allowed. Black holes grow by pulling in matter, but that process has limits. As gas spirals into a black hole, it heats up and emits radiation. That radiation pushes outward, creating pressure that resists further infall. This balance is known as the Eddington limit. It defines the maximum rate at which a black hole can accrete matter without the radiation pressure blowing away the incoming gas. For a black hole growing at the Eddington limit, the timescale to reach supermassive scales is long, too long to explain what we were seeing. Astronomers tried to reconcile this. Maybe the early black holes were fed more efficiently. Maybe gas reservoirs in the early universe were denser, allowing faster accretion. Maybe mergers happened more frequently, combining black holes into larger ones more quickly. These adjustments helped, but they were not enough. Even pushing the models to their most optimistic limits, the numbers did not work. The black holes were still too big, too early. Something was missing. Either our understanding of black hole growth was incomplete, or the formation process itself was fundamentally different in the early universe. This is where the problem stood before James Webb. A mystery lodged firmly in observational data, resistant to conventional explanations. The early universe was supposed to be a simpler place. Fewer stars, less structure, more time needed for complexity to emerge. Yet it was producing the most extreme objects in the cosmos with shocking speed. The question was no longer just how supermassive black holes grow. It was how they could exist at all. James Webb was built to answer questions like this. Its infrared sensitivity allows it to peer further back in time than any previous telescope. Light from the early universe has been stretched by cosmic expansion into the infrared spectrum. Invisible to optical telescopes, but perfectly suited to Webb's instruments. When Webb began operations, one of its primary goals was to study the earliest galaxies and the black holes within them. What it found exceeded expectations. Webb detected black holes at redshifts corresponding to just a few 100 million years after the Big Bang. These were not small or modest objects. They were already supermassive. Some weighed hundreds of millions of solar masses. Others reached into the billions, and they were actively feeding, accreting gas at prodigious rates, shining brightly as quasar. The light from these objects had traveled more than 13 billion years to reach us, offering a direct glimpse into the universe's first few 100 million years. And the picture that emerged was startling. These black holes were not growing slowly from stellar seeds. They were already giants. The timeline was too short for conventional growth. Even if a stellar mass black hole formed immediately after the Big Bang and accreted at the maximum possible rate, it could not reach the masses Webb was observing, not even close. The math did not work. The observations demanded a different explanation, and that explanation had been waiting in the wings for years, considered speculative but never ruled out. It was called direct collapse. Direct collapse is a mechanism that bypasses the slow growth problem entirely. Instead of starting with a stellar mass black hole and building up over time, direct collapse creates massive black holes in a single catastrophic event. The idea is elegant and extreme. Under the right conditions, a massive cloud of primordial gas could collapse directly into a black hole without ever forming a star. This would produce what is called a direct collapse black hole, or DCBH. These objects would be born massive, weighing tens of thousands to hundreds of thousands of solar masses from the start. With that head start, reaching supermassive scales becomes far more achievable within the limited time available in the early universe. The concept is not new. Physicists proposed direct collapse scenarios decades ago, but they were difficult to test. The conditions required for direct collapse are extreme and specific. The gas cloud must be massive, dense, and critically, it must remain free of heavy elements and avoid fragmenting into stars. Fragmentation is the usual outcome when gas clouds collapse. Gravity pulls the cloud inward, but turbulence, rotation, and cooling cause it to break apart into smaller clumps. Those clumps form stars. Once stars form, they enrich the gas with heavier elements through nuclear fusion. Those elements cool the gas more efficiently, making further collapse even more fragmented and star-dominated. Direct collapse requires preventing this entire sequence. The gas must collapse as a whole, smoothly and catastrophically, without forming stars along the way. For this to happen, the gas must be kept warm. Warm gas resists fragmentation because thermal pressure supports it against gravitational collapse into small clumps. But warm gas also resists collapsing into a black hole, creating a delicate balance. The key is finding conditions where the gas is warm enough to avoid fragmentation, but not so supported that it cannot collapse at all. This balance exists, but only under very specific circumstances. The gas must be primordial, composed almost entirely of hydrogen and helium with virtually no heavier elements. And it must be bathed in intense ultraviolet radiation from nearby sources, which heats the gas and suppresses the formation of molecular hydrogen. Molecular hydrogen is a coolant. It allows gas to radiate energy and cool down, which normally leads to fragmentation and star formation. By preventing molecular hydrogen from forming, the radiation keeps the gas warm and smooth, allowing a more massive, unified collapse. In the early universe, these conditions were rare but not impossible. The first generation of stars, known as population 3 stars, were massive and hot. They emitted intense ultraviolet radiation. If such a star formed near a massive gas cloud but not within it, the radiation could irradiate the cloud, suppressing molecular hydrogen formation and setting the stage for direct collapse. The cloud, unable to cool and fragment, would collapse as a whole. Gravity would compress the gas to extreme densities. At a certain point, the collapse would become unstoppable. The gas would plunge past the point of no return, and a black hole would form. Not a stellar mass black hole, but a massive seed weighing tens of thousands of solar masses or more. This process is rapid. Once the collapse begins, it proceeds on a timescale of hundreds of thousands to a few million years. Compared to the billions of years required for conventional growth, this is instantaneous. And once the seed black hole forms, it can begin accreting gas from its surroundings. With a much larger starting mass, it can grow to supermassive scales far more quickly. A black hole that starts at 100,000 solar masses only needs to grow by a factor of 10,000 to reach a billion solar masses. A stellar mass black hole starting at 10 solar masses would need to grow by a factor of 100 million. The difference is transformative. James Webb's observations provided the first strong evidence that this process actually occurred. The black holes Webb detected were not just massive. They exhibited properties consistent with having formed through direct collapse. Their host galaxies were young, with relatively little star formation. The black holes themselves appeared to be growing faster than their galaxies, dominating the mass budget in a way that suggested they formed first and the galaxy assembled around them. This inverts the traditional picture where galaxies form first and black holes grow later. In the direct collapse scenario, the black hole is the anchor. It forms early, grows quickly, and shapes the galaxy's evolution from the beginning. Webb also observed the environments around these black holes. The gas compositions, temperatures, and radiation fields were consistent with the conditions required for direct collapse. High radiation environments, low metallicity gas, and the evidence of rapid, smooth collapse without significant fragmentation into stars. These observations aligned with theoretical predictions, lending credibility to the direct collapse hypothesis. For the first time, we had direct evidence that supermassive black holes could form on timescales as short as 100 million years, bypassing the slow accretion process entirely. But direct collapse is not the only mechanism at play. The early universe was a complex environment, and multiple pathways to supermassive black holes likely coexisted. Some black holes probably did form from stellar seeds and grew through unusually efficient accretion. Dense gas reservoirs, frequent mergers, and sustained feeding episodes could accelerate growth beyond normal limits. Others may have formed through runaway collisions in dense star clusters, where stars repeatedly collided and merged until the cluster core collapsed into a massive black hole. Each pathway has strengths and weaknesses, and each leaves different signatures in the observational data. What makes James Webb's findings so significant is that they confirm direct collapse as a viable and perhaps dominant mechanism for early supermassive black hole formation. This resolves a long-standing mystery. It explains how the universe could produce such massive objects so quickly, and it opens new questions about the interplay between black holes and galaxies in the early cosmos. One of the most striking implications is that supermassive black holes may have played a far more active role in galaxy formation than previously thought. In the conventional picture, galaxies form first, assembling from smaller structures that merge and grow over time. Black holes appear later, forming at galaxy centers and influencing their surroundings, but not driving the overall process. Direct collapse changes this narrative. If massive black holes can form early, before significant galaxy assembly, they become central players from the start. Their gravity pulls in gas, triggering star formation and shaping the galaxy's structure. Their radiation heats and ionizes the surrounding medium, influencing how gas cools and collapses. In some cases, their energy output might even suppress star formation, regulating galaxy growth and preventing runaway star formation. This creates a feedback loop. The black hole forms, grows rapidly, and begins influencing its environment. That influence shapes the galaxy, which in turn feeds more gas into the black hole, sustaining its growth. The two systems co-evolve, each shaping the other. This is not a new idea. Feedback between black holes and galaxies is well established in the modern universe. But Webb's observations suggest this feedback began far earlier than expected, shaping the universe's first galaxies and setting the stage for everything that followed. Another implication involves cosmic reionization. Reionization is the process by which the universe transitioned from a neutral state, filled with hydrogen atoms, to an ionized state, where most hydrogen was stripped of its electrons. This transition occurred between roughly 400 million and 1 billion years after the Big Bang. For decades, astronomers assumed reionization was driven primarily by the first stars and galaxies, whose intense ultraviolet radiation ionized the surrounding gas. But early supermassive black holes, particularly those powering bright quasars, could have contributed significantly. Their radiation output dwarfs that of individual stars, and a single quasar can ionize vast regions of space. If supermassive black holes were common and active in the early universe, they may have played a major role in reionization, altering the universe's structure and evolution on cosmic scales. Webb's data also challenges our understanding of black hole demographics. How common were these early supermassive black holes? Were they rare anomalies, or did most early galaxies host them? The observations suggest they were more common than expected. Many early galaxies show signs of active black holes, implying that the conditions for direct collapse occurred frequently enough to populate the early universe with massive seeds. This has profound implications for our models of structure formation and cosmic evolution. Yet, many questions remain unanswered. Direct collapse requires specific conditions, and we do not fully understand how often those conditions were met. What fraction of early black holes form through direct collapse versus other mechanisms? How did the formation pathway influence the black hole's subsequent growth and its relationship with the host galaxy? And what happened to these black holes over cosmic time? Did they continue growing, eventually becoming the giants we see in the centers of modern galaxies? Or did some stall, remaining as intermediate mass black holes that we have struggled to detect? Webb's observations also raise questions about the seeds themselves. If direct collapse produces black holes weighing tens of thousands of solar masses, where are these intermediate objects today? We have detected stellar mass black holes and supermassive black holes, but intermediate mass black holes remain elusive. If they exist, they should be relatively common, left over from direct collapse events that did not grow further. Their absence, or at least their scarcity in current observations, suggest either that they are difficult to detect or that nearly all of them continued growing. Both possibilities have implications for our understanding of black hole evolution. There is also the question of diversity. Not all early black holes grew at the same rate or under the same conditions. Some may have formed in relatively isolated environments, growing slowly and steadily. Others formed in dense, turbulent regions where gas was abundant and mergers were frequent, allowing rapid growth. This diversity would create a population of black holes with different masses, spins, and histories, each shaped by the unique conditions of its formations and environment. Webb's observations are beginning to reveal this diversity, but much remains to be understood. One of the most exciting aspects of Webb's findings is what they imply about the future of black hole research. For decades, studying the early universe was limited by the capabilities of our telescopes. We could detect distant objects, but resolving details was difficult. Webb changes that. Its sensitivity and resolution allow us to study early black holes in unprecedented detail. We can measure their masses, accretion rates, and radiation spectra. We can analyze the composition of the gas around them and map the structure of their host galaxies. This level of detail was unimaginable even a few years ago. Webb is also detecting black holes that are not powering bright quasars. These are quieter, less active objects that previous telescopes would have missed. This expands our understanding of the black hole population in the early universe, revealing a more complete picture. Some black holes grow rapidly and shine brightly. Others grow more slowly or intermittently, remaining faint and difficult to detect. Both types are important for understanding how supermassive black holes form and evolve. As Webb continues its mission, it will detect even more early black holes. Each new detection refines our models and tests our theories. Some observations will confirm existing ideas. Others will reveal surprises, forcing us to rethink assumptions and explore new possibilities. This is how science progresses. Observations drive theory, and theory guides observations, creating a feedback loop that deepens our understanding over time. But Webb is not working alone. Other telescopes and instruments contribute to this effort. Ground-based observatories study nearby black holes, providing context and comparison. Gravitational wave detectors listen for the mergers of black holes across cosmic time, offering insights into their population and evolution. Radio telescopes map the jets and outflows from active black holes, revealing how they interact with their environments. Each instrument provides a piece of the puzzle, and together they build a comprehensive picture of black holes across the universe's history. The discovery that supermassive black holes can form in as little as 100 million years is not just a technical finding. It is a paradigm shift. It changes how we think about the early universe, the formation of structure, and the role of black holes in cosmic evolution. It suggests that the universe is capable of producing extreme objects far more quickly than we imagined, and that the processes shaping the cosmos are more diverse and dynamic than our models assumed. This finding also highlights the power of modern astronomy. 50 years ago, black holes were purely theoretical. We had equations and predictions, but no direct evidence. Today, we detect black holes routinely, measure their properties, and study their influence across the universe. We've imaged the shadow of a black hole, detected the gravitational waves from black hole mergers, and now traced their formation back to the universe's first few 100 million years. Each of these achievements seemed impossible at one time. Yet here we are, doing the impossible, again and again. The broader implications extend beyond astrophysics. The rapid formation of supermassive black holes challenges our understanding of how complexity arises in the universe. We often think of cosmic evolution as a slow, gradual process. Stars form, galaxies assemble, structures merge and grow over billions of years. But the early universe was also capable of sudden, catastrophic events that produced massive objects in geological instants. Direct collapse is one example. Supernova explosions, gamma-ray bursts, and neutron star mergers are others. The universe is not just slow and steady. It is also violent, sudden, and capable of producing extremes. This duality is important. It reminds us that the universe operates on multiple timescales simultaneously. Some processes take billions of years. Others happen in seconds. Both are real, both are important, and both shape the cosmos we observe. Understanding this duality requires us to think beyond simple narratives and embrace the complexity of reality. It also raises philosophical questions. If massive black holes can form so quickly, what does that say about the nature of the universe? Is it inherently unstable, prone to extremes and sudden transitions? Or is it simply more flexible and creative than we give it credit for? These questions do not have easy answers, but they are worth asking. They push us to think more deeply about the cosmos and our place within it. The detection of early supermassive black holes also has implications for the search for life. Black holes influence their surroundings in profound ways. They regulate star formation, shape galactic structure, and create conditions that can either promote or inhibit the formation of planets and life. If supermassive black holes were common and active in the early universe, they may have played a role in determining which galaxies became hospitable to life and which did not. A galaxy with an overly active black hole might have its gas stripped away, preventing star and planet formation. A galaxy with a moderately active black hole might experience regulated star formation, creating a stable environment conducive to life. Understanding this balance is crucial for understanding the conditions under which life can arise. There is also the question of whether life could exist near supermassive black holes. The intense radiation and gravitational forces make the immediate vicinity inhospitable, but farther out, conditions might be different. Some galaxies with active black holes also have vigorous star formation, creating regions rich in heavy elements and potential planetary systems. Whether life could arise and survive in such dynamic environments is unknown, but it is a question worth exploring. As we look to the future, the study of supermassive black holes will continue to evolve. Webb's observations are just the beginning. Future telescopes, both ground-based and space-based, will push even deeper into the early universe, detecting fainter objects and resolving finer details. Gravitational wave observatories will expand, detecting mergers of black holes across a wider range of masses and distances. Together, these efforts will build a comprehensive understanding of black hole formation and evolution across cosmic time. But there are also deeper questions that remain unanswered. What happens inside a black hole? Does anything survive the crossing of the event horizon, or is all information lost? How do black holes affect the fabric of space-time itself? And what role, if any, do black holes play in the ultimate fate of the universe? These are questions that push the boundaries of physics, touching on quantum mechanics, general relativity, and theories we have not yet fully developed. Supermassive black holes are some of the most extreme objects in the universe. They bend space-time, devour matter, and influence galaxies across billions of light years. They challenge our understanding of physics, force us to confront the limits of our theories, and reveal the universe's capacity for creating the extraordinary. The discovery that they can form in just 100 million years is a testament to the universe's creativity and to humanity's ability to uncover its secrets. For now, James Webb continues to peer into the early universe, uncovering more black holes, more galaxies, and more mysteries. Each observation adds another piece to the puzzle, bringing us closer to understanding how the universe evolved from a hot, dense state to the rich, complex cosmos we see today. And with each discovery, we are reminded of how much we still have to learn. The universe is vast, ancient, and full of wonders. Supermassive black holes are among its most enigmatic creations. They are not just objects to be studied. They are keys to understanding the universe's history, its structure, and perhaps its future. As we continue to explore, we move closer to answering the deepest questions we can ask. How did the universe come to be? How did it evolve? And what role do we as conscious observers play in this vast cosmic story? The fact that we can even ask these questions, let alone begin to answer them, is remarkable. We live in an age where the universe's most distant and ancient objects are within our reach. We can see light that has traveled for more than 13 billion years. We can detect gravitational waves from events that occurred when the universe was young. We can study the formation of black holes, galaxies, and stars in ways that previous generations could only dream of. And yet, for all that we have learned, the universe remains full of mysteries. Supermassive black holes are one. Dark matter is another. Dark energy is a third. Each of these phenomena challenges our understanding and pushes us to develop new theories, new tools, and new ways of thinking. This is the nature of science. It is not a fixed body of knowledge, but a process of inquiry, constantly evolving as we learn more about the world around us. The rapid formation of supermassive black holes in the early universe is a perfect example of this process in action. It started as a mystery, an observation that did not fit our models. It prompted new ideas, new theories, and new predictions. And now, with Webb's observations, we have evidence that one of those theories, direct collapse, is real. But this is not the end of the story. It is a new beginning. Each answer generates new questions. Each discovery opens new avenues of inquiry. What happens next depends on what we choose to explore. Do we focus on understanding the details of direct collapse, refining our models and testing them against observations? Do we search for intermediate mass black holes, the missing links between stellar and supermassive scales? Do we investigate the role of black holes in galaxy formation, cosmic reionization, and the evolution of structure? Or do we pursue all of these paths simultaneously, recognizing that each contributes to a fuller understanding of the universe? The answer, almost certainly, is all of the above. Science is not a linear process. It is a web of interconnected questions, each informing the others. Progress in one area often leads to breakthroughs in another. A discovery about black holes might reveal something about dark matter. An insight into galaxy formation might illuminate the nature of dark energy. This interconnectedness is one of science's greatest strengths. It means that no question is isolated, and every discovery has the potential to reshape our understanding in unexpected ways. For those who study the universe, this is an exciting time. We have the tools, the data, and the theoretical frameworks to tackle some of the deepest questions ever asked. We are living in the golden age of astronomy, a period where observations and theory are advancing hand in hand, revealing the universe in ever greater detail. The discovery that supermassive black holes can form in 100 million years is just one example of what is possible when curiosity, technology, and determination come together. But this progress also comes with responsibility. The universe is not ours to exploit or ignore. It is a shared heritage, a cosmic tapestry that connects us all. The more we learn about it, the more we realize how interconnected everything is. The atoms in our bodies were forged in stars. The elements that make up our world were created in supernova explosions. The very fabric of space-time that we study is the same fabric that we inhabit. We are not separate from the universe. We are part of it. This perspective is humbling. It reminds us that we are small, fleeting beings in a vast and ancient cosmos. But it is also empowering. It shows that we are capable of understanding our place in the universe, of uncovering its secrets, and of appreciating its beauty. The fact that supermassive black holes can form in just 100 million years is a testament to the universe's dynamism. The fact that we can discover this is a testament to our own potential. As we move forward, we carry with us the knowledge that the universe is full of surprises. It is more complex, more dynamic, and more wonderful than we ever imagined. And every time we think we have it figured out, it reveals something new, something that forces us to rethink, to question, and to explore further. This is the essence of discovery. It is not about finding final answers. It is about embracing the journey, following the evidence wherever it leads, and remaining open to the unexpected. Supermassive black holes forming in 100 million years. Direct collapse creating massive seeds in the universe's infancy. Early black holes shaping galaxies and reionizing the cosmos. These are not just scientific facts, they are stories, narratives that describe how the universe works, how it came to be, and how it continues to evolve. And like all good stories, they are full of tension, conflict, and resolution. They challenge us, surprise us, and ultimately expand our understanding of what is possible. The universe is waiting. There are more black holes to find, more galaxies to study, more mysteries to unravel. And with each new discovery, we come a little closer to understanding the cosmos and our place within it. The journey is long, the challenges are great, but the rewards are beyond measure. Because in the end, understanding the universe is not just about knowledge, it is about connection, wonder, and the realization that we are part of something far greater than ourselves. What makes the James Webb discoveries particularly profound is not just what they reveal about the past, but what they suggest about processes we cannot yet see. For every supermassive black hole detected in the early universe, there are likely dozens more hidden behind dust, obscured by intervening gas, or simply too faint for even Webb's sensitive instruments to capture. The population we observe represents only the tip of a much larger phenomenon. These visible giants are the brightest, most actively feeding members of a population that may have been far more numerous than we currently recognize. This has implications for our understanding of cosmic structure formation. If supermassive black holes were common in the early universe, their collective influence would have been substantial. Each black hole pumps energy into its surroundings through radiation and powerful jets. This energy heats gas, drives winds, and can either trigger or suppress star formation depending on the local conditions. Multiply this effect across thousands or millions of early black holes, and you begin to see how they could have shaped the universe's evolution on the largest scales. The energy output from these early black holes may have contributed to solving another puzzle: the missing satellites problem. Simulations of galaxy formation predict far more small satellite galaxies around large galaxies than we actually observe. Something must have suppressed the formation of these smaller structures. One possibility is that feedback from early supermassive black holes heated the gas in small, dark matter halos, preventing it from cooling and forming stars. The black holes, in effect, sterilized regions of space that might otherwise have hosted dwarf galaxies. This would explain the discrepancy between simulations and observations, linking black hole formation directly to the large-scale structure of the universe. But there is a delicate balance here. Too much feedback and galaxies might not form at all. Too little and galaxies would form stars too rapidly, exhausting their gas supplies and burning out early. The universe we observe sits in a sweet spot where black holes provide just enough feedback to regulate galaxy formation without shutting it down entirely. This balance suggests a deep connection between black holes and galaxies, a relationship that has been evolving since the first 100 million years after the Big Bang. Webb's observations also shed light on the diversity of black hole growth pathways. Not all early black holes followed the same trajectory. Some grew rapidly through sustained accretion, gorging on dense gas reservoirs and shining as brilliant quasars. Others grew more sporadically, experiencing bursts of activity separated by long periods of relative quiescence. Still others may have formed but never grew significantly, remaining as intermediate mass relics that we struggle to detect today. This diversity reflects the chaotic, dynamic nature of the early universe, where conditions varied dramatically from one region to another. The growth history of individual black holes is encoded in their properties. Fast-growing black holes tend to have higher spins because the accreted gas carries angular momentum. Slowly growing or merger-dominated black holes may have lower spins or more complex spin histories. By measuring the spins of early supermassive black holes, astronomers can infer how they grew, distinguishing between smooth accretion and episodic feeding or mergers. Webb's spectroscopic capabilities are beginning to enable these measurements, adding another dimension to our understanding of black hole evolution. Another critical aspect of Webb's findings is what they reveal about the seeds of supermassive black holes. Direct collapse produces seeds weighing tens of thousands to hundreds of thousands of solar masses, but other mechanisms produce different seed masses. Stellar mass black holes start at perhaps 10 to 100 solar masses. Dense stellar clusters might produce seeds weighing hundreds to thousands of solar masses. Each pathway leaves a different imprint on the final black hole population. By studying the mass distribution and properties of early black holes, astronomers can work backward to infer which formation mechanisms were most important. Early indications suggest that multiple pathways coexisted. Some black holes show properties consistent with direct collapse. Others appear to have grown from smaller seeds. The universe, it seems, explored multiple solutions to the problem of building supermassive black holes. This is typical of cosmic evolution. Rarely does nature settle on a single pathway. Instead, it experiments with many, and the relative importance of each depends on local conditions and cosmic history. The connection between black holes and their host galaxies is another area where Webb's observations are transforming our understanding. In the nearby universe, there is a tight correlation between black hole mass and the properties of the galaxy's central bulge. This suggests that black holes and galaxies co-evolve, each influencing the other's growth. But when and how did this relationship begin? Webb's observations suggest it may have started very early, with black holes forming first and galaxies assembling around them. This inverts the traditional picture and raises new questions about causality. Do black holes shape galaxies, or do galaxies shape black holes? The answer may be both, in a complex feedback loop that began in the universe's first 100 million years. There is also the question of what happened to black holes that formed but did not grow. If direct collapse was common, it should have produced a population of intermediate mass black holes that never reached supermassive scales. Where are these objects? Some may lurk in the centers of small galaxies or globular clusters, difficult to detect because they are not actively accreting. Others may have been ejected from their host galaxies through gravitational interactions, wandering the intergalactic medium as isolated, invisible objects. Detecting these missing black holes is one of the next major challenges for astronomy. Gravitational waves may provide the key. When black holes merge, they emit gravitational waves whose properties depend on the masses and spins of the merging objects. Future gravitational wave observatories, particularly space-based detectors like LISA, will be able to detect mergers involving intermediate mass black holes. If these events are common, they will confirm that a substantial population of black holes formed in the early universe and never grew to supermassive scales. If such mergers are rare, it would suggest that most early black holes either grew rapidly or were destroyed through other processes. The implications extend beyond black holes themselves. The rapid formation of supermassive black holes tells us something fundamental about the conditions in the early universe. It tells us that gas was abundant, that certain regions were bathed in intense radiation, and that the right conditions for direct collapse occurred with some regularity. This provides constraints on models of the early universe, helping us understand how matter was distributed, how the first stars formed, and how structure began to emerge from the primordial smoothness left over from the Big Bang. It also connects to the broader story of cosmic chemical evolution. The first stars were made of pure hydrogen and helium. They contained no heavy elements because none had been created yet. When these stars exploded as supernovae, they enriched the surrounding gas with the first heavy elements: carbon, oxygen, iron, and others. These elements changed how gas could cool and collapse, influencing the formation of later generations of stars and black holes. The transition from a pristine, metal-free universe to one enriched with heavy elements was a critical phase in cosmic history. Supermassive black holes formed during this transition, and their properties reflect the conditions of that pivotal era. Webb's ability to measure the chemical composition of gas around early black holes provides direct evidence of this transition. Some black holes sit in regions that are still relatively pristine, consistent with direct collapse scenarios. Others are surrounded by gas that has already been enriched, suggesting they formed later or in regions influenced by earlier star formation. This chemical archaeology allows us to reconstruct the timeline of the early universe with unprecedented precision. The study of early supermassive black holes also intersects with questions about the nature of dark matter. Dark matter provides the gravitational scaffolding on which all cosmic structure forms. Galaxies form in dark matter halos, and black holes form at the centers of those galaxies. The properties of dark matter, such as its particle mass and interaction strength, influence how halos form and merge. By studying the early universe where these processes were just beginning, astronomers can test models of dark matter and constrain its properties. Deviations from expected behavior could signal new physics, pointing toward exotic forms of dark matter or even modifications to gravity itself. There is also speculation, still highly tentative, that some supermassive black holes could have primordial origins. Instead of forming from collapsed gas in the early universe, they might have formed directly from density fluctuations in the moments after the Big Bang. These primordial black holes would have existed before any stars formed, seeding the universe with massive objects from the very beginning. While evidence for such objects remains weak, they have not been ruled out. If confirmed, primordial black holes would represent a completely different formation mechanism, one rooted in the physics of the Big Bang itself, rather than in the behavior of gas and stars. What makes all of this so compelling is the convergence of evidence from multiple sources. Webb provides optical and infrared observations, revealing the light from early black holes and their host galaxies. Gravitational wave detectors provide information about black hole mergers across cosmic time. Radio telescopes map the jets and outflows from active black holes. X-ray observatories study the hot gas around black holes, revealing accretion processes and feedback effects. Each instrument contributes a unique perspective, and together they build a comprehensive picture that no single telescope could achieve alone. This multi-wavelength, multi-messenger approach is the future of astronomy. It recognizes that the universe reveals itself in different ways at different wavelengths and through different phenomena. Light tells one story. Gravitational waves tell another. Neutrinos, cosmic rays, and other messengers add additional layers. By combining all of these, astronomers can triangulate on the truth, building models that are robust and consistent across multiple lines of evidence. The philosophical implications of these discoveries should not be overlooked. The rapid formation of supermassive black holes challenges our intuitions about time and change. We tend to think of the universe as evolving slowly, with complexity building gradually over eons. And in many ways, this is true. But the early universe was also capable of sudden, dramatic transformations. In just 100 million years, a tiny fraction of cosmic history, the universe went from a relatively smooth state to one containing supermassive black holes weighing billions of solar masses. This demonstrates that the universe is not just patient. It is also explosive, capable of rapid transitions that reshape everything. This duality between slow evolution and sudden change is fundamental to understanding cosmic history. It applies to stars, galaxies, planets, and perhaps even to life itself. Evolution proceeds gradually most of the time, punctuated by rare but transformative events. Supermassive black holes forming through direct collapse are one such event. Others include supernova explosions, gamma-ray bursts, and the mergers of neutron stars or black holes. Each of these events releases enormous energy in a short time, creating conditions that would never arise through gradual processes alone. Recognizing this duality helps us appreciate the richness of the universe. It is not a static, unchanging place, nor is it entirely chaotic and unpredictable. It is dynamic, evolving according to physical laws that allow both stability and transformation. Understanding these laws and how they give rise to the universe we observe is one of the great intellectual achievements of our species. As Webb continues its mission, it will undoubtedly uncover more surprises. Each observation has the potential to confirm existing theories or overturn them entirely. This is the nature of exploration. We venture into the unknown, guided by our best understanding, prepared to revise that understanding when evidence demands it. The willingness to change our minds in the face of new data is what separates science from dogma. It is what allows knowledge to grow and deepen over time. The discovery that supermassive black holes can form in 100 million years is a milestone, but it is not an end point. It is a waypoint on a much longer journey, one that will continue for generations. Future telescopes will push even deeper into the early universe, detecting the very first black holes and galaxies. Future theories will refine our understanding of direct collapse, accretion, and feedback. Future observations will reveal the full diversity of black hole populations across cosmic time. And future generations will look back on Webb's discoveries the way we look back on the discoveries of Hubble, as foundational achievements that opened new windows on the universe. James Webb has given us a glimpse into this story, revealing chapters we had never read before. But the story is far from over. It continues, unfolding across billions of years and countless events, and we, as observers and participants, get to witness it, to study it, and to share in the wonder of discovery. That is a privilege, a responsibility, and an invitation to keep looking, keep questioning, and keep exploring. The universe is waiting. There are more black holes to find, more galaxies to study, more mysteries to unravel. And with each new discovery, we come a little closer to understanding the cosmos and our place within it. The journey is long, the challenges are great, but the rewards are beyond measure. Because in the end, understanding the universe is not just about knowledge, it is about connection, wonder, and the realization that we are part of something far greater than ourselves. If this journey fascinates you, if the mysteries of the cosmos spark your curiosity, then stay with us. There is so much more to explore, so much more to discover. The universe is vast, and we have only just begun to scratch the surface. Subscribe, stay curious, and let's continue this journey together, because the best discoveries are yet to come.